One, two, three. We're going to talk about logistic growth today. So, logistic growth is a little bit different than exponential growth or decay because it starts as exponential growth, but then it stops becoming exponential and kind of changes a little bit. So, what we learned yesterday was that when the rate of change is directly proportional to the amount of the substance, so for example, there were problems where we had the size of a tumor or the rate of change of the tumor was directly proportional to the size of the tumor. We also had some Newton's law of heating and cooling. So it was the temperature of a cup of coffee was proportional to the difference between the temperature that it was and the surrounding temperature. So situations like that, population or the amount or the rate of change, whatever, that thing would grow in an exponential or decay in an exponential way. Uh, it's reasonable for population growth in the short term, but then what ends up happening is we have food shortages or habitat limitations, living space, infighting, lots of different things that could happen that could constrain or limit the amount that a population grows. For example, another situation would be a spread of a rumor. So let's say you are spreading a rumor at Wabansie Valley High School. Um, there is a limit to the amount of people that can know the rumor because there's only a certain amount of people at Wabansie Valley High School. So if you spread a rumor, the rumor spreads fast at the beginning and then eventually it starts slowing down because you only have a certain amount of people that are at the school. So logistic growth starts off exponentially. So notice there's some exponential growth, and then it changes concavity and reaches the maximum amount that we can possibly have. So in this case, what we have is we have some sort of horizontal asymptote that appears as you approach this maximum. So this is an example of a logistic curve in terms of a graph. The differential equation dp over dt, or dp dt, that's equal to some constant times the population times the difference between the carrying capacity and the population. Notice the carrying capacity of a population is the maximum amount or maximum sustainable population that you have. And then we also have this equation, which is the general equation of a logistic growth function. Um, and I will explain that at the end of the video as kind of a bonus as to how we get from the differential equation to here. But that's not something that we've spent a lot of time talking about, at least in the year that I'm making this video. So the quantity P, the population, is growing at a rate that is proportional to the product of the population and the difference between the current population and the carrying capacity, which is also known as the room available for further growth. So if the capacity is, for example, 800 and the current population is 700, then we only have 100 uh, potential more room for growth in that population. Now let's get to some examples. Number one, given the differential equation and initial condition, let's discuss the following questions. According to the model, what is the carrying capacity? Well, according to what we saw earlier, the carrying capacity is C in this case. So if we're looking at this model, the carrying capacity is 100. Find an equation for P. So once again, we'll talk about the calculus that gets us that equation later, but we know that this equation is P equals the carrying capacity, which we know is 100, divided by 1 plus A, which is some constant, times e to the negative C, which is the carrying capacity, which is 100, times K, which they tell us is 0.005 in this problem, times T. So this is our equation. We have to solve for A. The good news is they gave us an initial condition, and not only is that good news, it's really, really good news because they actually give us what happens when t is 0. So when t is 0, that means p is 20. So I have 20 equals 100 over 1 plus a times e to the 0. Notice that when t is 0, that whole thing becomes e to the 0. E to the 0 is 1, so it ends up being pretty simple. I multiply 1 plus a over to the other side, and then I distribute, so I get 20 plus 20a equals 100. If I subtract 20 and divide by 20, I get a equals 4. So my equation here is going to be p equals 100 over 1 plus 4 e to the negative 100 times 0.005, which would be negative zero point 0.5 t. So that's our equation. What appears to be the limit of the function as t approaches infinity? So in order to get that, let's take a look at what the function actually looks like, and we will graph that. So if we're looking at this function, um, I'm going to simplify this to be negative zero point 0.5. If we zoom out a little bit, it appears that this function levels off right around 100, which is exactly what we said was going to happen. Um, so when we look at this, this is the same value as the carrying capacity. So the limit as t approaches infinity is p equals 100, which is the carrying capacity or maximum amount, the maximum population. The y-intercept of the function is 20, and we already knew that because they told us that it was 0, 20. But if we look at the graph again, it's pretty clear that that's also true. So the y-intercept is at 0, 20. And what we're going to do now is verify the exact time and population of the point where the population is growing the fastest. So in order to do that, let's take a look at this. It appears that this is somewhere in this area. Okay. So in order to do that, what we're going to do is we're going to take a look at this differential equation that we had. So dp dt equals 0.005 p times 100 minus p. Now I'm going to do it with y's and x's, but technically the p is the y, so that might be a little confusing. But if we take a look at this differential equation, what we're trying to do is figure out when the growth rate is the fastest. So that means dp dt has to have a maximum. Now we could take the derivative of this function and set it equal to 0. And when we do that, what we're going to find is we're going to find that the maximum is at 50, comma 12.5. Now 50 is actually representing the y value here. I know I said this already, but x is really representing y. 50 is our maximum speed, basically, that we have of this growth rate. So the growth rate is maximized at 50, which appears to be where this concavity changes. So if we're looking at the function that we have here, if we're looking at the function, this function is going to have the population be growing the fastest when the differential equation that we have here has a maximum, and that would be at the point of concavity change of this function. So that is occurring at 50. I'm sorry, 50 for the y. Um, and when we look at the function, when we look at 50, we should probably set y equal to 50 and then figure out what that is. So if we set y equal to 50, we find the intersection at 2.773. So the time is 2.773, and there's no context for this problem. So we don't know if it's years or whatever, but that's the exact time and population where the population is growing the fastest. Notice that 50 is exactly half of the carrying capacity. This is always true. So the rate at which the logistic growth graph is growing the fastest for population is always at half the carrying capacity. That is probably something you're going to want to write down. Okay, let's move on. Problem 2. If we look at problem 2, the spread of a disease through a community can be modeled with a logistic equation. P equals 800 over 1 plus 25 e to the negative 0.1 t. Carrying capacity, that shows up here. So that's 800. What does it mean in terms of the community? So that means we can have a variety of different explanations. First of all, 800 is what happens after we get a quarantine, or maybe even the community has 800 people in it and everybody got the disease. So there's some way that we end up containing the disease where everybody that has the disease is kind of quarantined until they're either dead or immune to it, not passing it on anymore. It kind of depends on how severe the disease is, I guess. Write a differential equation describing the rate at which the disease spreads with respect to time in days. So in order to do that, we have dp dt, and that is equal to kp times 800 minus p. So we basically have to figure out what k is. Well, in order to find k, we know that negative 0.1 is equal to negative c times k. So c was 800. So negative 0.1 is equal to negative 800 times k. So that means k is equal to 1 over 8,000. So my final equation is going to be dp dt equals 1 over 8,000 p times 800 minus p. And I know I wrote that really sloppily, so I'll kind of move that so you can see it. Part C, how many people are infected when the disease is spreading the fastest? This is 400. You can discover this either with calculus by finding the maximum of this differential equation, which is 800 kp minus kp squared, taking the derivative, and you find out that the maximum of a parabola is always at the midpoint. So the midpoint of the two vertices. So if not the vertices, the midpoint of the two x-intercepts. So if the x-intercepts are at 0 and 800, we would average them and find out that it's 400 people. So that's something that you should probably memorize. Problem 3. A nature preserve can support no more than 400 giraffes. 60 giraffes were known to be in the preserve in 1990. Assume the rate of growth is, I'm reading what the problem used to be before I changed it. Okay. Oh, actually, assume the rate of growth is 10 giraffes per year when there are 100 giraffes in the preserve. There, I can just read off the screen. Assume the rate of growth is 10 giraffes per year when there are 100 giraffes in the preserve. So let's find a differential equation. Differential equation is going to be dp dt equals k times p times 400 minus p. We know that it's 400 because that is the carrying capacity that they stated. Now, we are going to assume the rate of growth is 10 giraffes per year. So dp dt is 10 when there are 100 giraffes in the preserve. So k is unknown. We're trying to find that. P is 100, and 400 minus p is 300. So I need to solve here. And when I solve, I end up with k equals 10 over 30,000, which is 1 over 3,000. So my dp dt that I have is 1 over 3,000 times p times 400 minus p. That's part A. Part B, find a formula for the population at any time t. So if I want to do that, I know my population equation is going to be the carrying capacity divided by 1 plus A times e to the negative C KT. Notice that they tell me um, that there are 60 giraffes in 1990. We will make the year 1990 t equals 0 in this problem. So I can say 60 equals 400 over 1 plus a. Notice that e to the 0 is 1. Multiply over, so I get 60 plus 60a equals 400. Subtract 60, divide by 60, I get 340 over 60, which is 17 thirds. So my final answer is P equals 400 over 1 plus 17 thirds times E to the negative C K T. And I didn't write that down, so I guess I'm just going to have to figure out what it is. So K is 1 over 3,000, and C is 400. So that ends up being 4 over 30, which is negative 2 over 15. I probably could have wrote that, but sorry. So negative 2 over 15 times T. What is the population of gorillas when the number of gorillas is increasing most rapidly? We should probably know that is 200 gorillas. Sorry, giraffes. I forgot to change that part of the problem. And how long will it take for the giraffe population? Sorry, guys. How long will it take for the giraffe population to reach 50% of its carrying capacity and 75% of its carrying capacity? Well, in order to do that, I'm going to take a look at the graph because I don't really want to actually solve that by hand at the moment, since you guys can probably solve it by hand anyway. So if I look at these equations, what I would end up with is, well, I probably have to zoom out a little bit more to see where it crosses 200 and 300. By the way, notice that it does level off at 400. So it looks like I have these two intersections. So when it's at 200, which is 50%, I am at 13.010 years, which is about 2003 in the problem's context. And then 75% of the capacity is at 21.249 years, which is in about 2011. You can figure out where it gets to about the amount of years that it will take to get to the exact capacity. That's when you get above 399.5 or so. So around 64 years it would take in order to get to the maximum amount of giraffes. So I'll write down the answers here and then I'll move on to the bonus. If you don't really want to stick around for the bonus, you don't have to. Um, uh, but it ended up being at 2003 and 2011 as the answers there. By the way, you could solve letter D by setting P equal to 200 and P equal to 300. And solving for T, so you'd multiply over, divide by 200, subtract 1, multiply by 3/17, then take a natural log. I mean, it's things that you can do algebraically. I just didn't feel like that was necessary at this time.